Welcome to The Explainer. We're about to unlock a surprising energy secret hidden inside one of the most common machines in our cities, the elevator. We're going to break down some real-world data to see how one simple upgrade can make a huge difference.
I mean, we all ride them, but have you ever really thought about how much power it takes to lift all that weight, floor after floor, all day long? This isn't just a box on a cable, you know? It's a major energy consumer in any tall building.
Okay, so let's get right into it and look at the hidden cost of a simple elevator ride. We're talking about those intense bursts of energy that happen every single time the doors close and the car starts to move. So check this out. Just to get a fully loaded car moving upwards, a standard elevator motor has to pull a massive amount of current. The test data shows a peak demand of over 36 amps. That's a huge jolt to a building's entire electrical system, and it happens over and over and over again. Now, here's a thought. What if we could capture and reuse all the energy that's normally just wasted every time an elevator slows down or goes down? Well, this is where some really cool technology offers a pretty brilliant solution. And here it is, the hero of our story, the supercapacitor regenerative energy storage unit. Now think of this thing as a sprinter, not a marathon runner. A battery, right? It stores a lot of energy and lets it out slowly. A supercapacitor is the opposite. It can absorb and release huge bursts of power almost instantly. And that makes it absolutely perfect for the non-stop start and stop life of an elevator.
Yeah, picture it like a high-speed sponge. When an elevator breaks or goes down, its motor actually acts like a little generator, creating what's called regenerative energy. The supercapacitor just soaks that right up. Then the next time the elevator needs a big power boost to get moving, it just wrings out that stored energy to help the motor, which dramatically reduces the pull from the grid. Pretty smart, huh?
Okay, so that's the theory, but does it actually work? This is where it gets really exciting. We're not dealing with hypotheticals here. We're looking at hard data from a direct, side-by-side comparison. Let's see what really happens when you install one of these units.
First, let's look at the most demanding scenario you can think of. A completely full elevator car, packed with people, heading straight up. This is where the motor works its absolute hardest.
And wow, look at the immediate impact. That peak current we talked about, it plummets from over 36 amps down to under 24. That is a massive reduction in that initial electrical stress, just like that. And this shows you exactly how that drop in peak current translates into overall savings. The total energy needed for a full round trip is cut, saving precious watt hours on every single journey.
Okay, let's move to a more common situation, a 50% load. This is where the weight of the car and the counterweight are nearly balanced, which is pretty much typical for daily use.
You know, what's interesting is that in this balanced state, the system actually becomes even more efficient. The energy for a round trip drops from 10 watt-hours to just 8. That's a 20% saving in the most frequent use case.
Finally, what about an empty car doing a bunch of short runs? You know, like a service elevator, or during off-peak hours. This scenario involves a lot of starts and stops, which is normally super inefficient.
And just look at this. In this frequent start-stop test, the savings are the most dramatic of all. The supercapacitor unit slashed total energy use from 36 watt-hours all the way down to 26. This is where that capture and release cycle really shines.
So what's the big takeaway here? What do all these numbers add up to? Well, the data reveals a really clear and compelling pattern about where this technology is the most effective.
This quote from the source analysis just says it all. The more an elevator starts and stops, the more opportunities the supercapacitor has to capture and redeploy that energy. It actually thrives on the very activity that is usually the most wasteful.
So let's just recap those savings, because this is where the pattern becomes so obvious. At a full 100% load, the system delivers a solid 12.5% in total energy savings.
But then, under those more typical, balanced 50% load conditions, that saving jumps up to an impressive 20%. And in the most demanding stop and start scenarios, the savings peak at a remarkable 27.8%. The technology literally gets more efficient the harder the elevator works. Isn't that incredible?
But the benefits here aren't just about saving money on the electricity bill. The impact is much, much broader than that.
By softening those harsh electrical spikes, the technology reduces the wear and tear on critical, expensive components, like the actual traction machine used in this test. That could potentially extend the elevator's entire lifespan.
And on a larger scale, it means less strain on the public power grid, cleaner power for the entire building, and a direct reduction in carbon emissions. For any company, that's a tangible boost to their sustainability goals
and their green credentials.
And why this matters is that it shows how targeted, intelligent innovations can have a profound impact on the energy footprint of our everyday lives. A smarter elevator really does mean a smarter building.
This leaves us with a final thought to chew on. If this principle works so well for elevators, where else in our world, from trains and cranes to factory robotics, can we apply this powerful idea of capturing and reusing energy that was once simply wasted?